Hello, and welcome to this lesson on the carbon-carbon double bond in alkenes. In today's lesson, we will understand that the carbon-carbon double bond is the functional group of alkenes. Then we will explore how this functional group determines the chemical properties and reactivity of alkenes. So far, we've discussed the general properties of alkenes. We've seen that functional groups are specific groups of atoms within molecules that are responsible for the characteristic chemical reactions of those molecules. Building on this foundation, we will explore how the carbon-carbon double bond in alkenes specifically influences their properties and reactivity. Firstly, recall that alkenes are hydrocarbons, which means they are compounds made up of hydrogen and carbon atoms. The defining feature of alkenes is the presence of at least one carbon-carbon double bond. This carbon-carbon double bond is what we refer to as the functional group of alkenes. Functional groups are specific groups of atoms within molecules that determine how those molecules typically react. The presence of the carbon-carbon double bond gives alkenes their characteristic unsaturated nature. Unlike alkanes, which only have single bonds and are therefore saturated, alkenes can open up their double bond to add new atoms to their structure. This capacity to add atoms defines their unsaturated nature. One of the most important chemical reactions alkenes undergo is called an addition reaction. During an addition reaction, the double bond between the carbon atoms is broken and new atoms are attached to these carbons. This transforms the double bond into a single bond and typically results in the formation of a new product. For example, when ethene, an alkene, reacts with bromine, a halogen, the product is dibromoethane, demonstrating how the alkene adds the bromine atoms by breaking its double bond. To visualize this, think of an alkene molecule with its carbon-carbon double bond as a flexible hinge. This hinge can open up, allowing new atoms to attach themselves, which changes the molecule's structure and properties. We'll talk about this a bit more in the next lesson. Understanding this, we see that alkenes react very similarly due to the consistent presence of the carbon-carbon double bond across this group of compounds. This predictable behavior is seen throughout the homologous series of alkenes, meaning that members of this series, for example, ethene, propene, butane, will undergo similar types of reactions. The carbon-carbon double bond in alkenes is relatively reactive, which means it can easily be transformed by various chemical reactions. Aside from addition reactions with halogens, alkenes can also react with hydrogen halides like HCl, water and hydrogen, each time undergoing an addition reaction that breaks the double bond and forms new single bonds. One significant application of the reactivity of the carbon-carbon double bond is in polymerisation, where small alkene molecules, monomers, join together to form long chains, polymers. For instance, the polymerization of ethene results in polyethene, a common plastic. Because of their reactivity and ability to form various compounds through addition reactions, alkenes are crucial intermediates in the synthesis of a multitude of organic compounds. This knowledge will allow us to grasp how these simple yet powerful reactions lead to the production of a vast array of important materials and chemicals in everyday life. In today's lesson, we delved into the importance of the carbon-carbon double bond as the functional group of alkenes, which determines their chemical properties and reactivity. We learned that alkenes are unsaturated hydrocarbons due to the presence of this double bond, which allows them to undergo addition reactions. These reactions involve breaking the double bond and adding new atoms, resulting in the formation of new products. Additionally, we touched on the significance of polymerisation, where small alkene molecules join to form long-chain polymers. This understanding highlights the reactivity and versatility of alkenes in synthesizing various organic compounds and their industrial applications. This lesson has provided a solid foundation for further exploration of organic chemistry and the role of functional groups in chemical reactions. Watch the rest of the GCSE chemistry course at Sophos Education.